Hi and welcome back. So in the previous video we introduced technological progress into our economy, and we said it would be captured through the impact it has on labor, such that labor now becomes effective labor as opposed to just looking at labor as we did in the previous chapter. We also looked at the interaction between output per effective worker versus capital per effective worker. So in this video, we'll first look at the interaction between output and capital in an economy where there is a technological progress. So now that we have the element we need to think about the determinants of growth after the introduction of technological progress. Our analysis in this section will be parallel to that of chapter 11, or rather parallel to the one we had in chapter 11. So in chapter 11, if we could just do a brief recap, we looked at the dynamics of output per worker and capital per worker. Here we will look at the dynamics of output per effective worker and capital per effective worker. So if you may remember, in chapter 7, we characterized the dynamics of output per effective worker using a figure that showed us three relations. So relation 1 was the relation between output per worker and capital per worker, the relation between investment per worker and capital per worker, and the third relation was a relation between depreciation per worker, which we said was equivalent to the investment per worker needed to maintain a constant level of capital per worker and capital per worker. So the dynamics of capital per worker and by implication output per worker were determined by the relation between investment per worker and depreciation per worker. So in this section, we'll be looking at the same relations. However, now we'll look at output per effective worker and capital per effective worker, and investment per effective worker and capital per effective worker. And lastly, depreciation per effective worker and capital per effective worker, or rather, the investment per effective worker needed to maintain a constant level of capital per worker. So if we would remember again in chapter 11, we said depending on whether investment per worker was greater or smaller than depreciation per worker, capital per worker increased or decreased over time, and so did output per worker. So we shall follow the same approach we had in chapter 11 here. Again, with the difference of the fact that we are now looking at output, capital, and investment per effective worker rather than per worker. So under the same assumption used in the derivation of the solo growth model in the previous chapter last week, we begin our assumption by stating that investment is given by savings, and savings is basically the ratio of income that is saved, which is basically stating that investment is given by private savings. So as we did before, we divide both sides by the number of effective worker, since now we're looking at effective worker. If you remember very well, in the last chapter last week, we divided by worker instead of effective worker. So doing so, it shows us that investment per effective worker is equal to the savings per effective worker. So this is pretty straightforward as it follows from what we covered last week. So in essence, it basically tells us that we are trying to see or look at investment and savings per effective worker. So from the equation 2 that we had, where it shows us that output per effective worker, in the previous video, we saw that output per effective worker is a function of capital per effective worker. So if we denote our output per effective worker by its expression from the equation, from this equation, would and substitute it in this investment equation, then it would show that investment is basically a function of savings as a function of capital per worker, or simply investment per worker is a function of savings per worker. So we are now in a position to represent the relationship between investment per effective worker and capital per effective worker in a figure similar to that which we showed in the previous chapter. Again, just like before, we have a curve that represents investment, or rather represents the relation between investment per effective worker and capital per effective worker, as well as a curve that represents output per effective worker and capital per effective worker, as well as the required investment, which before we said it was basically depreciation, since we said investment is basically equals to depreciation before. So the question that we are equipped to ask now is, what level of investment per effective worker is needed to maintain a given level of capital per effective worker? Or rather, what level of investment per effective worker is needed to maintain a steady state level of capital per effective worker, or level of growth? So in the previous chapter, chapter 11, we said that for capital to be constant, investment had to be equal to depreciation of the existing capital stock. Here the answer is slightly more complicated. Why is this? This is because now we allow technological progress, and therefore A increases over time. The number of effective workers also increases, since the number of active workers is AN, and if technological progress increases, it means that A increases over time. Therefore, maintaining the same ratio of capital per effective worker, which is basically K over AN, requires an increase in capital stock K that is proportional to the increase in the number of effective workers. This means that for K over AN to increase proportionately, these two have to increase at the same time. But let's look at this condition more closely. So before we continue, let's pin down some ideas here. So again, depreciation will be still represented by delta, and the rate of we'll let the rate of technological progress be GA. So this is basically the growth rate of technological progress, meaning that technological progress grows at the rate of GA, and the rate of growth of population and therefore number of workers will grow with GN, which is the growth of number of workers. This is because we still assume that the ratio of employment to the ratio of population remains constant. So the number of workers also grows at the same rate as population at GN. So together, this assumption imply that the growth rate of effective labor is basically equals to, so AN will grow at the rate of GA plus GN, such that if the number of workers is growing at 1% per year and the rate of technological progress is growing at 2% per year, and therefore AN will be equals to 3%. So following this assumption, it follows that the level of investment required to maintain the level of capital per effective worker is given by this relation here, which basically says investment is equals to depreciation of capital plus the growth rate of effective worker into capital. So we can simplify it as this ratio. So the depreciation of capital is required to maintain the capital stock constant. It means that investment must be such that it replaces the capital that has been invested in the previous year. So if depreciation is 10%, then investment must be at least 10% of capital stock to remain in the proportion of the initial capital stock that is lost as a result to depreciation. And above that depreciation, an additional amount of GA plus GN is required to ensure that the capital stock keep pace with the rate of growth of effective labor. Or rather, it is required to ensure that the capital stock increases at the same rate as the effective labor. So what does this mean in reality? It means that, for example, if depreciation rate is 10% and the growth rate of effective labor, which is GN plus GA, is 3%, then investment must be 13% of the capital stock to ensure a constant level of capital per effective work, meaning that the new investment, which will translate into capital, must cover what has depreciated and what is needed to maintain growth. So if we divide equation 3 by the number of effective worker, it provides information about the amount of investment per effective worker required to maintain a constant level of capital per effective worker, which is given by this relation here. So the level of investment per effective worker required to maintain a constant capital per effective worker is given by the upward sloping straight line in our curve here, this one. And the slope of the curve is given by this fraction here, which is depreciation plus growth of technological progress and growth of population. So to pin down the ideas about the dynamics change of the capital output over the long run, we look back into this curve here and explain from this curve. And we will do that in the next video. Thank you.